So, the other thing I'm going to talk about now is Slurm and ALPS on Piz Daint. Now, many of you in the room may know a lot about this already, and therefore this may be going over material that you're quite happy to walk out of the door if you find that this is something that you just don't need to hear again. But there are certain little issues with how to run on this machine, and certain things just to make sure that on any of the machines, the Cray machines that we're running on, that you don't make some mistake and get poor performance. So we've deployed Slurm about 2 years ago as a site-wide resource management system, and this means that moving from one system to the next should be relatively straightforward, including moving from Monte Rosa. I don't know why that's in a lighter font. Main commands, tell me if this is anybody not familiar with Slurm enough to know what these main commands do. No, okay. I'll rush through therefore. So we have SQ, scancel, sbatch. I always like to tell people about it in that order so that you know how to cancel a job before you've badly submitted it. And then other commands that we'll just have a quick look at are salloc, and this is because of what I mentioned about internal versus external logging. I won't really talk about scontrol, but that's a very powerful tool. And sacct to see what jobs have been running and what happened to them. This is something that we use quite a lot, particularly to see which nodes we ran on. And therefore, it's easier for us to be able to say, well, if somebody's got a problem, somebody's had a bit of an issue, well, did we have a bad node? Which we do from time to time on these machines, get nodes that just have problems. Just so you know about SQ, so people know how it works or what it's telling you. So firstly, the jobs, the order of the jobs. So it tells you jobs in their order of priority. The top thing is the next one to have the highest priority to run. Then it will go down and say which jobs can't yet run due to dependencies, and then at the bottom it lists the running jobs, and you'll notice that it always says which the very last job is the one that will finish first. So you can actually just go straight to the bottom of here and see how many nodes are available in whatever time. Sometimes looking at these running jobs and so on can be useful to see if you can get a backfill slot. So if, for example, you could see that the top job was requiring a large number of nodes, a few nodes were going to become available here soon, but then the job this one depended on wasn't going to be available for a while, you might be able to find that I can sneak in there. You can customize the output of SQ with SQ format to get different things along here and put that in your bash script. And I've changed, of course, the names of these jobs so they all look quite better than they did before. So sbatch, well, we put down output error, time, job name. It's important to put a time in and an accurate time because you, again, can fit in those backfill slots. Specifying the task requirements with sbatch is the thing that I just want to mention here, particularly on this machine, because we've just been migrating from an older version of Slurm to a newer version of Slurm, the first to be deployed on this type of system. So you can just go along and ask for X nodes, and you're free then to use them as much as you want with MPI and OpenMP mixed, apart from, as things stand today, you need to specify the flag if you want hyperthreading. If you don't say you want hyperthreading and you try to use it with your aprun line, it won't work. That's something we'll find out whether or not is something that we've just installed, put in ourselves, or whether it's something that actually we can get around. You can specify processes, how many threads, and so on. And as we said, telling Slurm how to use hyperthreading. So the specific options, the one that we're particularly interested in is this thing down here. N tasks per core says whether or not you're going to use hyperthreading. If you say, I want to use 2 tasks per core, and tasks in this case, there's a little bit of a terminology issue, because at one point, Slurm is talking about tasks in terms of MPI processes, and that's why CPUs per task is how many threads per task, effectively. And then here, the thing we've had to overload is the tasks per core, which causes confusion if you think, what happens to the threads? But it was something we needed quickly to be able to put into place. So you put in those options and you ask for a certain number of processes, a certain number of threads, and then there's an interaction of sbatch with ALPS. Because Slurm doesn't manage the nodes on this system. On clusters, Slurm manages the nodes. It knows all about the nodes. Here, it has to do a little bit of a discussion, a diplomatic negotiation with the ALPS system that Cray employs. And the set of options that you put in determine what you're allowed to do with your nodes. If you ask just for a set of nodes, you have this more freedom about, oh, I'll use so many processes and so many tasks, as long as the multiplier doesn't exceed the number of cores that you actually got on your nodes. And, of course, that you don't ask for something like 40 threads on a node when you've only got space for 16. But if you actually ask for tasks and threads, then the request you've made to ALPS means that ALPS gets a little bit picky at times and says, you didn't quite ask for that. It may be that if I ask for 64 tasks, each with 4 threads, it's the same multiplier as 32 tasks, each with 8 threads. But ALPS may say at the aprun time, claim exceeds reservation. But if you ask for a simple set of nodes, you're OK. You still need that hyperthreading, as mentioned. So how does this all work? Got a little batch script up here. Batch script will be submitted onto Daint's external logging node. Important, it's the external logging node. Goes to the Slurm server. It then picks out one of the front-end nodes. And there's 4 front-end nodes, I believe, we have on this system that will then say, that's where your script actually runs. It then passes the script over, and it's the script from below here all runs on one of these front-end nodes. It's no longer on that external login node. You're actually internal to the machine. This is vitally important because otherwise, aprun doesn't work. If you try doing aprun on the external login node, it will just tell you, I don't know what you're talking about. That's not one of my commands. So you have to be internal. And then there will be an unwind procedure when the batch system kills your job. So the main options to aprun generally match ones that we have as options to sbatch. Aprun, of course, being analogous to MPI run, srun, etc. So processes, n tasks is n, CPUs per task, and so on. For the n tasks per core is -j, but we have this issue at the moment, as I mentioned, that this one you just have to repeat what you've done before. OK. So I mentioned about hyperthreading with the -j option or the n tasks per core, and the question then is, should you use it? So there are some heuristics that we can start to throw in about whether or not this might be a good idea or not. So one of the things, we can go back even in time and see what other applications look like on previous machines using symmetric multi-threading or hyperthreading. And it's basically, you tend to find that if you have an application where different cores, different threads will be doing different things at different times, then you may be able to use different functional units. And that's where hyperthreading comes into play. Because if the floating point unit is busy, but the integer unit is not, and you want to use the integer unit, you may be able to get some speed up. It's more important, actually, normally, further away from that in terms of whether something's using the memory bandwidth and something's using the floating point units. So, but if you've got something where you're just trying to do, say, dense linear algebra and everybody wants the same unit, you tend to not find that to be too good. But the real point is, try it yourself. It's one of those things where you should just try it and see what happens. The same as we say with compilers. Try out the different compilers, put on the fast flags, the O3s and so on, and see which one gives you the best performance. Here, try hyperthreading and see whether it works, as long as you have sufficient memory available on the hyperthreads for your application. One thing to be aware of, though, is MPI scaling, and that relates to if you've got a pure MPI code and you decide to throw in hyperthreading, you might start to find that some of your processes, yes, they really can overlap, and you can get some better performance, but the problem is you've now moved 2 times further along on the MPI scaling curve. And so every gain that you may get there, if you're at the limit of your scaling, you may actually lose by the time you come down to weighing up MPI scaling curve versus the increased performance you get. And you should be comparing what can I get out of an X number of nodes, not about any particular thing about the processes themselves. If you need to ask for it, then remember to put the -J2 option on. Now, we've been doing this work in terms of getting hyperthreading and CPUs per task and all the rest, so that the aprun man page, which says there's by default one task per physical core, matches with what we have with Slurm's default way of working and what's on the Slurm man pages, the sbatch man pages. And all of this is to actually make it so that when you come to the aprun line, wherever possible, you don't need to re-specify the same thing. So a typical way that this might work is down here. I ask for 64 tasks, 4 CPUs per task. So I'm going to run with 4 OpenMP threads, which unfortunately I don't have in my batch script, but I should have done. I then repeat this on the aprun line, N64D4. Okay. Now, if I go and change the batch script, I have to change it further down. If I happen to have a batch script that wants to do an aprun, then there's a quick something else and another aprun and so on. I have to go through the whole script and change all this. And it can become a little bit of a pain. So Cray provided this -B option to aprun a year or two ago now. And this says, OK, if this information was provided for you by the batch system, reuse it. So if you use --nodes equals and just ask for the nodes, ALPS doesn't know really what you wanted. But if you do ask for these specifics, ALPS does know what you wanted, and so therefore it will save you the trouble of writing all those numbers in again. There are a couple of provisos. One is that on our current implementations, within Slurm, and we're not sure whether this is actually a thing that has to do with ALPS or with Slurm or just the way we've written things. If you ask for 17 tasks, so you're asking for 16 on one node and 1 on the next, the way our setup goes, it actually asks for 32 tasks. And then -B doesn't work because you only wanted 17. Therefore, this will only work if you're actually asking for whole numbers of nodes in terms of you are going to use all the resources on the nodes from the processes and threads point of view. You can also get more fine-grained control with aprun. So up until this -J option that we just talked about, which is available on the XK that we have here, not the XE. We haven't upgraded an operating system to the level available at the moment. If you put -J1 on a Bulldozer-based AMD system, then it will then just give you one task per Bulldozer module. It will skip over the other cores. But up to now, including on Rosa as it stands at the moment, instead you have to get your hands dirty and actually do something yourself. You could do -D, but if you want to get but that's not necessarily going to work too well if you also want to use some threading. So with CC being the way to get more fine-grained control, there are a set of different options, non-numanode and CPU, to say whether you want no control and so on. But there are some more advanced options. So this is significant if you want to use that Intel compiler that you'll hear about tomorrow. You have to get clever if you want to actually be able to use this effectively. -CC says, place me processes and threads in specific places at specific times. This notation was introduced, I think, about a year ago, specifically, with a colon in the middle. And it says, each one of these relates to a process and the threads that it creates. So here we have 2 processes, and this tells ALPS, it tells the runtime, when you create that process, run the first process on core 0 and the second on core 8. Then, when the first thread that's created, let it run anywhere. That's the X. And then the next ones that are created, pin them to core 1, core 2, core 3. If you're running a threaded application, therefore, what this will do is on a normal application, such as with the GNU compiler, it would say, first process is running on core 0 and the first thread, therefore, on core 0, the master thread. Then it would let the other one run wherever it wanted to, and then thread 2 would be on core 1, and so on and so forth. Why would you want to do that? Well, you wouldn't. But the difference is that the Intel compiler, the first thread that it creates in an OpenMP parallel region is not a real thread as far as we're concerned. For the application, it's a shepherd thread. And then you need to really get into this ugly way of working. You have this option with aprun. Another option that's of significance with aprun is the -R option for core specialization. It's more significant really in some ways when looking at the XE6. And this says if you start to get jitter or other issues with your application, then you might want to say, look, on a browser node, I have 32 cores. I don't need all those 32 cores. Give one of them up. Let the operating system find its way over to the furthest point on the node effectively and run there and not get in the way of my application. This is also significant if you put the right flags on and the right compilation, and you have a lot of MPI asynchronous communication going on with iSends and iReceives and so on. You can also have this extra core that you've given up be used for an extra thread that just tries to move those asynchronous operations forward while you're getting on with something else. On the XC30, instead of giving up a physical core, you get a hyperthreaded core. This means that normally you wouldn't even notice. If you haven't asked for hyperthreading, but you've asked for all 16 cores that therefore are available to you, you can still use -R1 and it will find a hyperthread to run this on. And then there are also things such as the -SS option to ensure memory is only allocated on the NUMA node on the task is running. This is another one that you might just want to throw into your application when you're running and see if it makes a difference. Sometimes it makes a difference to actually have this pin things definitely onto my NUMA node. And then there are some other options that you could get even finer grained NUMA control. So how does aprun map the CPUs to the physical and virtual cores? Well, on this machine, aprun goes through and it maps the processors or threads round robin on the physical cores. And the naming, the numbering of the cores, and you can see that in the Linux output when the thing is booted, is it numbers physical cores first. So it goes through physical cores, 7 of them on the first socket, then it jumps over to the other socket and names the next 8 to 15, and only then does it go back to the first socket and then start numbering the other cores. This is good because it means if you ask for 16 processors or threads and they start to get pinned, they get pinned 1 per physical core rather than overlapping on the virtual cores. If you're on an Interlagos-based system, instead, it will fill up the bulldozer modules one by one, and that's not so good. But let's say on this XC30 you want to run only 8 cores per node. Perhaps you need some more memory or something, 4 gigabytes instead of 2 gigabytes per process. You won't get the best performance if you just ask for task per node 8, put -N8 onto your aprun line, because it's still doing what I mentioned here. It just maps your processors onto the physical cores as it sees them. And so that means by default, you've said, I only want 8 processors, but they will all run on the first socket and the second socket, all that lovely memory bandwidth, all those nice vector operations and so on. None of it will be touched. It will all just be left idle. This is bad here. It's even worse if you're on the XE6 system, where if you did the same with 8 processors, they'd all be on the first die, and you'd really be restricted. And there are people who do this, because this isn't an obvious thing to do. But you therefore have to specify either a depth or find some other way of spreading out your processors so they go on to the correct places. You could use the -CC option, but just specifying -D to push things further apart would also be an effective way of doing this. So I've mentioned before salloc, and I've mentioned before the internal login nodes, and this is where the two things come together. So we tell you to do everything on those external login nodes, apart from you can't do this. Aprun needs to be running on the internals of the machine. It can't actually run from an external machine because there's no interaction with ALPS. ALPS is looking around on the machine only. This may change in the future with some ideas about bridges and so on across from external logging nodes that Cray are currently thinking about. But as things stand at the moment, this is the way it has to work. And therefore, you need to be able to launch, first of all, get yourself on the machine, and only then start Slurm and say, can I have some node? Now, the times you might want the interactive batch job are sometimes tools actually require it, such as our debugging tools, where they need to be able to directly attach to the aprun command. So a debugger typically you would launch as something like, what if it was total view, which we are now phasing out, total view, aprun minus little a, and then all the other options. And it's basically saying, I want you to debug aprun and anything beyond it. The other time you might need it is sometimes it's just useful for development. Now, we don't encourage you to do this very often, but sometimes if you've got to do quick turnaround times on small numbers of nodes, you might want to get a salloc session and then just keep launching the aprun as you play around, as you experiment, so to speak, with ideas. If you want to do this, you have to jump directly onto one of those internal logging nodes, Daint 01, 02, or 03. Then you can ask for a salloc session. And the salloc takes the same options as the batch thing for requesting. Now, the important thing as well about a salloc session is do one only if you're pretty sure that there's going to be some spare nodes available. Okay, and they're already available, because otherwise you'll start the session. It won't run, it won't allocate you anything, but you'll probably have gone off for a cup of coffee or maybe to lunch by the time it comes back, and then the nodes sit there doing nothing. The other thing is immediately give it up as soon as you've finished and return things to the pool, because you'll be charged for this. Another thing to mention is Slurm dependencies. So sometimes you may actually you may have a lot of jobs and one's dependent on the next and so on and so forth. So for example, if you're going to run some molecular dynamics application and the simulation you want to run is going to actually take you 8 weeks of continuous runtime for the same thing, then you don't want to submit a job and then wait the next one, that's finished, and then submit the next. You can put in dependencies, and the two most important ones are saying after OK, dependency, so it shouldn't say minus minus, but minus minus dependency equals after OK and a job ID. You can get a whole stream of these things. If anything fails, then you have to go back and repair the bad work. But if they're all succeeding quite happily, then you'll be able to just leave them to run. And this is something that also can be quite useful for you. And the final thing is something that we're using a lot at the moment to trace where we've got issues on the system, and that is to use the sacct command, the saccount system command. And this will tell you what jobs you've run recently. You can look a few days back, and you can see which ones completed, failed, cancelled, and so on and so forth. By adding extra options to this, you can also find out node lists and other things as to where you ran specifically. That means that therefore you can also do a reverse mapping and say, that job ran particularly slowly compared to the other one, as I mentioned before. Was that because I went across groups, or was I, rather than being pinned within a group, etc., etc.? So there are a number of options to see your previous usage that sacct is very useful for. So that's all I'm going to talk about today, those two sessions, and that means that you can all enjoy the not so warm weather anymore that was there earlier in the day. Any questions about Slurm and its interaction on this machine?